See, given that T is a bounded linear operator from a normed space X onto a normed space Y. So it is given that T is onto. It is also given that there is a positive B such that norm of Tx greater than or equal to B norm X for all X belongs to capital X. We want to show that T inverse exists and is bounded. So first we will show that T inverse exists. A necessary and sufficient condition for the existence of T inverse is T is 1, 1 and onto. We have T is onto, so it's sufficient to show that T is 1, 1. So for suppose Tx1 equal to Tx2. So this implies Tx1 minus Tx2 equal to 0. Implies T of x1 minus x2 equal to 0. So by linearity of T. Therefore, 0 is equal to norm of T of x1 minus x2. So if something is 0, its norm is also 0. And by the given condition, see x1 and x2 are elements of the normed space capital X, means it is a vector space capital X. So x1 minus x2, which is x1 plus minus x2, is also a member of capital X. So this is a member of capital X. And for all X belongs to capital X, norm of Tx greater than or equal to B norm of X. We have, there is a fixed B such that, so this is greater than or equal to B, a positive B into norm of x1 minus x2. So this implies norm of x1 minus x2 is less than or equal to 0 because B is positive. Now norm of x1 minus x2 less than or equal to 0 means the only possibility is norm of x1 minus x2 equal to 0 implies x1 minus x2 equal to 0. Consequently, x1 equal to x2, T is 1, 1. Therefore, T is 1, 1 and onto. Therefore, T inverse exists. So this part is proved. Now to show that it is bounded. And we know that, see, T is a function from X to Y, which is onto. And T inverse is a function from Y to X. To show that T inverse is bounded. So what we want to show is, so we want to show that T inverse is bounded. So for that, it's sufficient to show that norm of T inverse is less than infinity or less than or equal to K, or norm of T inverse is bounded. And norm of T inverse is norm of T inverse Y by norm of Y, supremum of norm of T inverse Y by norm of Y, where Y not equal to 0 belongs to capital Y. Supremum of these. So in order to find this number, we start with the Y belongs to capital Y. So let Y belongs to capital Y. And we know that T is onto. Therefore, T inverse Y belongs to capital X. Since Y is onto, since T is onto, or since T inverse exists, T inverse is a function from Y to capital X. See, for Y belongs to capital Y, T inverse Y belongs to capital X. And there is a given condition that for all X belongs to X, there is a fixed B, such that norm of Tx greater than or equal to B into norm of X. We apply that to this particular X, T inverse Y. So by the given condition, norm of Tx greater than or equal to B into norm of X for all X belongs to capital X. So in particular, for this X, norm of Tx, T inverse Y greater than or equal to B norm of X, that is B norm of T inverse Y. Now T inverse is identity out because T inverse is the inverse of T. So therefore norm of Y greater than or equal to b into norm of t inverse y. So making b to the left side and norm y to the right side, what we get is, therefore, see, we have this norm of y greater than or equal to b norm of t inverse y. See, this is true for all y belongs to capital Y since y is arbitrary. Therefore, norm of t inverse y by norm y is less than or equal to 1 by b. See, this is true for all y belongs to capital Y. Therefore, supremum also less than or equal to 1 by b. And supremum of this LHS is norm of t inverse. So norm of t inverse is less than or equal to 1 by b. Since b is a given fixed positive number, this is less than infinity. Therefore, t inverse is bounded.